Alright, let's take a look at a special case of a rational function where there is actually going to be a common factor that's present. And this actually will identify a scenario called a point discontinuity, also known as a hole. So I'm going to show you what this kind of looks like. If you actually factor out f of x here, it's x squared minus 4 over x plus 2. We want to sketch this. Well, if you factor this out, you can actually write this as x plus 2 times x minus 2 over x plus 2. And you can notice that there is a common factor. Just off the bat here, we can understand that there is a very important restriction. If x can belong to all real numbers for your domain, but x cannot equal negative 2. Okay, and if x is negative 2, look what happens. We basically get negative 2 plus 2 here is 0, and negative 2 plus 2 here is 0. So we get 0 over 0. This actually does not represent a vertical asymptote. This is actually what we call an indeterminate state. Right, and the indeterminate state actually represents something called a point discontinuity. So it's a missing point, and the point discontinuity is also known as a hole, aka a hole. Okay, so this is a missing point in the function. Now, if we wanted to actually solve for this, we can actually simplify the expression, and we can see that it looks like x minus 2. We know that x minus 2, if we're looking at f of x is equal to x minus 2, this should be a linear function, right? So you can think about this as slope-intercept form, mx plus b. So this is the point, the y-intercept is 0 and negative 2, and the x-intercept, if I just let f of x equals 0, we get x minus 2 is equal to 0, so x is equal to 2. So the x-intercept is 2 and 0. Based on this, we can actually draw out a line. Now, we stated that f of negative 2 would not exist, right? But in our simplified state, we can actually plug this in. F of negative 2 should not, therefore, equal negative 2 minus 2, which is negative 4. So the point that doesn't exist is negative 2 and negative 4, and this represents the hole, right? So the way you can figure out the hole, the value of the hole, you simplify the function first, you get the simplified expression of the function. So in this case it's x minus 2. We know that x cannot equal negative 2, but if I do plug it in, then if x cannot equal negative 2, then negative 2 and negative 4 shouldn't exist. So this is where the hole exists. And I'll show you guys what the hole looks like. But if the negative 4 doesn't exist, then the range of this function, right, y belongs to all real numbers, but y shouldn't be equal to negative 4. Good? So it shouldn't also be equal to negative 4 because there will be a hole of the function, right? And because it's a linear function, we would expect to see that there is going to be one y value for a given x value. Now this would be different if you have a parabola, but there's only going to be one y value for a given x value. Now if you wanted to sketch this, right, we can understand there is no asymptotes, right? A hole is not an asymptote. Okay, so there's no asymptotes because this is basically going to be a linear function. And if we want to find an intercept, well, we already just found the intercept because it's a linear function. So the intercepts are correlated with this linear function. Okay, so we already did part C. And let's take a look at what the sketch will look like. Okay, so I'm just going to create my grid system here. Okay, so on my grid system, I'm going to plot the x-intercept 2 and 0, somewhere here. And we also have y-intercept 0 and negative 2, somewhere here, right? And all we have to do now is we construct a line, but we need to note that, so this is our line, right? But we need to note that negative 2 and negative 4 is our hole. So this is actually a missing point. Do you guys see that? Right, so this is actually a missing point. So that's how we can represent a hole. We just do this open circle here, right? I think I overly exaggerated it, but right, so we have this missing circle here, and that represents a hole. But beyond that, it's basically will look like a linear function, right? And that's basically what our graph will look like. Right, so it's pretty straightforward. Last thing we want to do here, let's describe our end behaviors. Right, as long as x does not equal negative 2, as x approaches negative infinity, as we go this way to the left, right, then y is going to approach negative infinity. And as x approaches positive infinity, as we're going this way to the right, y is approaching positive infinity. So opposite end behaviors is what it looks like. And this is basically how we can analyze a function that does have a point discontinuity, or also known as a hole. Alright, let's take a look at another rational function where the degree of the numerator is 1 higher than its denominator. Here we have a trinomial, a quadratic trinomial, x squared minus 9x plus 20 divided by x minus 4. Okay, so we want to sketch this based on domain range, asymptotes, intercepts, and behavior. Now, first thing before you actually even attempt to sketch this thinking, okay, there's going to be an oblique asymptote here, what you need to do is first let's factor the numerator. Let's see if it's actually factorable. And this, in fact, here this is factorable, right? So the x squared minus 9x plus 20 can be factored out as x squared minus 4x minus 5x plus 20, right? That's because we want two numbers to add up to -9, then multiply to 20. This is a decomposition, factoring by decomposition. You can also consider this product and sum rule. And you get x minus 4 minus 5x minus 4, and you get x minus 5 times x minus 4. Okay, so this is basically the factored form of this. And you can actually notice that there is a common factor, right? There's x minus 5 times x minus 4 over x minus 4. So you can actually notice that f of 4 here is going to be a restriction because we get 0 over 0. This is an indeterminate state. This is also indicative of a hole that's being present, right? So this is something that you have to watch out for. So just by looking at the domain, x belongs to a set of all real numbers, but x cannot equal 4 because you'd be indeterminate, right? And in that sense, if we cancel this out and we simplified it, this is the function that we're going to be working with. Okay, so f of x is equal to x minus 5. Okay, now because we said that x cannot equal 4, f of 4 should not equal 4 minus 5, which is -1. It cannot equal -1, right? So 4 and -1 is the hole, is the point discontinuity. It's the point that doesn't exist. It's a break in the function. Okay, so this is a point discontinuity, and as a result, y belongs to all real numbers, but y cannot equal -1. So this is really important to understand because this is a linear equation, right? Because now you can see that the simplified expression is a linear equation, right? So that one y value will not exist. Having said this, we can understand that for part B, so this was part A, for part B, there are no asymptotes. There is a point discontinuity. There is a hole that exists at 4, -1. So now it becomes really straightforward, right? Because we have a linear function. So just by looking at your function x minus 5, f of x is equal to x minus 5, you can notice that the y-intercept, because this is slope-intercept form, y is equal to mx plus b, the y-intercept is 0 and -5. The x-intercept, on the other hand, we just let y equal 0, and we get x minus 5 is equal to 0, x is equal to 5. So the x-intercept is 5 and 0. Now let's sketch out this graph really quickly. Okay, so I'm just going to create a grid. Okay, so this is our grid, and I'm just going to plot these points out. Okay, so we have the y-intercept 0, -5, say it's somewhere here, and the x-intercept at 5 and 0, say it's somewhere here. Okay, this is 5 and 0, this is 0 and -5. Okay, let's just draw a grid let's draw the line in a different color. And this is what we'd expect. We expect, whoops, let's just make this line a little less deeper. This is what we'd expect. Okay, so you're gonna obviously use a ruler to draw this, right? However, we know that there's a hole at 4 and -1. So the hole would exist right here. So I'm just gonna make maybe we can just touched area here. So just get rid of that. Okay, so there's a hole at 4, -1. So there's a point that's here that shouldn't exist. Okay, so that's basically how we're going to attach it. Right, so you're obviously going to have a better sketch than mine is, but this is basically your line here. You should actually see a hole at that point, right? So that point doesn't actually exist. Okay, so keep this in mind, that's the whole, and this is basically your function. So this is basically an end. The end behavior of this is going to be the end behavior of a line segment. So as we look at the end behavior, as x approaches negative infinity, as we go this way, right, y will also go down this way. So y will actually approach negative infinity. This is an odd degree function. So thereby, you should have opposite end behaviors, right? As y approaches positive infinity, as you go this way for y, as x approaches positive infinity, as you go this way for x, y will approach positive infinity up here, right? So y approaches positive infinity. So that's the idea behind this. It's relatively straightforward in terms of a rational function and sketching it if you can see the presence of the whole. So make sure you, if there is a quadratic trinomial, that you factor first and then analyze. Alright, let's take a look at sketching another example of a whole found in a rational function. So here we can actually notice that the degree of the denominator is 1 higher than the degree of the numerator. If I factor this, let's use a different color here. So if I factor this, f of x minus 2, if I factor the denominator, we get x minus 4 times x minus 2, right? And you can use the decomposition method. Two numbers that add up to negative 6 that multiply to positive 8. Excuse me. And that can be negative 4x minus 2x plus 8. If I factor this out, you get x minus 4. If I factor out negative 2, you get x minus 4, and you get x minus 2 times x minus 4. Okay, so we understand that. Now, the next thing we want to do here is we can notice that there is a common factor, so we can cancel out the x minus 2. We can understand that f of 2 here would give us 0 over 0. This indicates an indeterminate state. Indeterminate states will indicate that there is the presence of a whole, right? So if we have a common factor, then we have a presence of a whole. Now the function that we're actually going to be working with is going to be f of x is equal to 1 over x minus 4. Okay, so it's going to basically be a reciprocal function. And if I wanted to analyze the domain range here, the domain excuse me, the domain here is x belongs to all real numbers, but x cannot equal 4. Okay, so x cannot equal 4. The range here, right, we have to, so this is our simplified expression, right, but we can also understand that x cannot equal 2 as well, right? So just because we cancel out doesn't mean we don't have to list it. As currently our domain here, x cannot equal 4, but we can also understand that f of 2 would give us 0 over 0, so x cannot equal 2. Now, looking at this is our simplified expression, so this is the function that we're going to be working with. There's going to be the presence of a horizontal asymptote. We can understand that this function can never be equal to 0, right? So as a result, y belongs to all real numbers, and y cannot equal 0. Okay. So having said that, we also understand that our restriction on our domain is going to be a vertical asymptote. However, we can understand that f of 4 here will give us 1 over 0, which is indicative of a horizontal asymptote. As long as you have c over 0, this tells you that you have, sorry, did I say horizontal asymptote? I meant vertical asymptote, right? If you have c over 0, this is indicative of a vertical asymptote. So we have a vertical asymptote at x is equal to 4. However, we don't have a vertical asymptote at x is equal to 2, right? Whenever you have 0 over 0, this is an indeterminate state, and as a result, we have a whole or a point discontinuity at x is equal to 2. Now, we want to figure out the equivalent y value. We know that f of 2 does not equal 1 over 2 minus 4. It wouldn't exist in the actual function. And that equivalent y value here is negative 1/2, right? So 2 and negative 1/2 will not exist, right? So the whole here is 2 and negative 1/2. Okay, so the whole will not exist, and we also have a horizontal asymptote at y is equal to 0. Okay, so keep that in mind. So using this all of these things, we can kind of sketch our function. We're going to be looking at our simplified expression, our simplified function, and let's take a look at some of our intercepts. So because we said that the horizontal asymptote y is equal to 0, the graph won't cross our x-axis, right? So we don't have to look for x-intercepts. So we're just going to find a y-intercept. So I'm going to let x equal 0. So I'm going to do f of 0 here is equal to 1 over 0 minus 4, which is negative 1/4. Okay, so you get negative 1/4. So the point here is 0 and negative 1/4. Okay, so that's the y-intercept. And now what you want to do here is you want to plot these points, right? So we have a vertical asymptote, we have a hole, we have a horizontal asymptote, we have a y-intercept, and we can understand that this is a reciprocal function. So let's place our grid here, and let's sketch the graph. Okay, so looking at our grid, I'm going to place my vertical asymptote, x is equal to 4. So let's place that here. Okay, so I'm just going to do the vertical asymptote in blue. Okay, so this is my vertical asymptote, x is equal to 4. We also have a horizontal asymptote, y is equal to 0, so that's basically going to be the x-axis. Let's do that in red. So guys, use a ruler for this. Right, so this is our horizontal asymptote, y is equal to 0. And we only have to plot our y-intercept, right? We have a hole at 2 and negative 1/2. So I'm just going to plot the hole really quickly. Let's do that in orange. So the hole here is 2 and negative 1/2. So 2 and negative 1/2. Let's say it's like somewhere here. Okay, well, it's going to be kind of hard to draw that out. Okay, so we're going to have a hole there, right? And we should have a point, the y-intercept is 0 and negative 1/4, right? So it's kind of hard to tell where this is on this grid. Okay, and if we follow the confines of the asymptotes, right, we're going to get something like that. Now this, once again guys, this is a sketch, so you want to have an actual idea of what the graph will look like. You should plot some test points. Okay, so yeah, I'm trying my best here to sketch this guy out, but right, so that's the idea. So this is one of our graphs, and the other graph here should kind of look like that. So you can do a series of test points. Alright, so that's our other graph here, right? And this whole, this point discontinuity of 2 and negative 1/2 does not exist. Okay, so that's basically it, right? So it's our rational function that doesn't, it has this hole here, it's a missing piece at 2 and negative 1/2, right? And if we wanted to look at our end behaviors, we could. So I'm just going to do my end behaviors out here in lime green. So if we're looking at our end behaviors, we can understand that if I'm going towards negative infinity here, right, as x approaches negative infinity, y will approach the horizontal asymptote from below, so 0 from below. As x approaches vertical asymptote from the left-hand side for negative, y also approaches negative infinity. And then in this case, as x approaches 4 from the right side, right, so as x approaches 4, the vertical asymptote from the right side, you can see that the trace in orange goes up, y goes to positive infinity, and as x approaches positive infinity, y will approach 0, or the horizontal asymptote from above. Okay, so this is the end behavior, and this is basically our a little spin-off of our example of point discontinuities or holes, right? You can see that we actually created a rational function, and this does take a little bit of time to kind of construct.